Imagine standing at the edge of an ocean so vast, so deep, that our entire Earth could sink into it and vanish without a trace. An ocean not measured in miles or kilometers, but in planetary radii, where pressure at the bottom would be millions of times greater than Earth's atmosphere, where water isn't just a surface feature, but the very essence of a world. This isn't science fiction. This is TOI 1452b. Just 100 light years from where you sit right now, astronomers have discovered a super-Earth with oceans potentially 30 times deeper than anything on our planet. A world where water might make up 30% of its entire mass. For comparison, Earth, our blue marble, has oceans that cover 71% of its surface. Yet water accounts for far less than 1% of our planet's mass. So how did this remarkably water-rich world form? What strange physics allows it to exist? And what might live in those unfathomable depths? The answers might just change everything we thought we knew about planets, water, and life itself. Welcome to our cosmic journey into one of the most perplexing mysteries in modern astronomy. I'm glad you've joined us for this deep dive into the enigma that is TOI 1452b, a super-Earth that pushes the boundaries of our planetary formation models. Before we begin our exploration, if you enjoy content that takes you to the edge of human knowledge and beyond, please consider subscribing to our channel and hitting that notification bell. Your support allows us to continue creating these in-depth cosmic journeys. Over the next few hours, we'll trace the discovery of this remarkable world, from the first hints of its existence to the latest revelations about its true nature. We'll examine why its water content appears surprisingly high compared to standard models. We'll explore the leading hypotheses that might explain this cosmic anomaly, from exotic ice phases to planetary migration. We'll also venture into the profound implications of such a world, what it means for our search for life beyond Earth, how it reshapes our understanding of habitable zones, and what it tells us about the diversity of planets in our galaxy. This is a journey perfect for pondering while you relax, work, or simply gaze at the stars, wondering what strange worlds orbit them. So settle in as we explore the deepest oceans in our cosmic neighborhood, and perhaps glimpse our own future. Our story begins, as many astronomical discoveries do in the 21st century, with a space telescope and a tiny dip in starlight. In 2018, NASA launched the Transiting Exoplanet Survey Satellite, or TESS. Unlike its predecessor Kepler, which stared fixedly at one patch of sky, TESS was designed to scan nearly the entire celestial sphere, focusing on the brightest nearby stars. Its mission: to find planets transiting across the faces of their host stars, causing minute but detectable dimming in their light. Among the thousands of stars TESS observed was TOI 1452, a small red dwarf star in the constellation Draco, the Dragon. Red dwarfs are the most common type of star in our galaxy, smaller, cooler, and dimmer than our Sun. Despite their abundance, they remained largely overlooked in early exoplanet searches because of their faintness. But TESS, with its sensitive instruments, could detect even the subtle signals from these cosmic lighthouses. Interestingly, TOI 1452 is actually a binary star system, two red dwarfs orbiting each other at a distance of about 97 astronomical units, roughly twice the distance between our Sun and Pluto. This initially complicated the discovery. Tess's cameras couldn't resolve which of the two stars was being orbited by the planet. Was the signal coming from the primary star or its companion? Determining this required careful follow-up observations with ground-based telescopes that could distinguish between the two stellar partners. Ultimately, astronomers confirmed that TOI 1452b orbits the primary star of the pair. In the data from TOI 1452, astronomers noticed something: a regular pattern of dimming that occurred every 11.1 days. This pattern suggested a planet was orbiting the star, passing between it and our telescopes with clock-like precision. The depth and duration of these transits provided the first clues about the planet's size, roughly 1.67 times the radius of Earth, a super-Earth. But size alone tells us little about a world's true nature. Is it rocky like our home? Gaseous like Neptune? Or something else entirely? To answer these questions, astronomers needed more data. They turned to ground-based observatories, including the Observatoire du Mont-Mégantic in Canada, equipped with the SPI-RO spectrograph, an instrument designed specifically to study red dwarf stars and their planets. Led by Charles Cadiel, a PhD student at the Université de Montréal, the team conducted follow-up observations that would prove crucial. Using a technique called the radial velocity method, they measured how much the planet's gravity pulled on its star, causing it to wobble slightly. This wobble, detected as tiny shifts in the star spectrum, revealed the planet's mass, approximately 4.8 times that of Earth. Now they had both the size and the mass of TOI 1452b. And that's when things got interesting. When astronomers determine a planet's radius and mass, they can calculate its density, how much matter is packed into its volume. This fundamental property offers vital clues about composition. Dense planets are likely rocky. Less dense ones might contain significant amounts of water, gas, or both. TOI 1452b's density came out to about 5.6 grams per cubic centimeter, with uncertainties of roughly plus 1.8. 1.6, roughly similar to Earth's approximately 5.5 grams per cubic centimeter. But here's the key. A super-Earth made purely of rock and metal like Earth should be noticeably denser due to stronger self-compression under higher gravity. The fact that its density is lower than expected for a pure rocky world points to lighter materials. And the most likely candidate? Water, but not just a little water. Not just oceans like Earth's. The calculations suggested that up to 30% of this planet's mass might be water, if the water world hypothesis is correct. For comparison, Earth, despite its blue appearance from space, contains less than 0.1% water by mass. Our oceans, impressive as they are merely a thin film on our planet's surface, averaging just 3.7 kilometers deep. If the estimates were correct, TOI 1452b's oceans could plunge to depths of over 100 kilometers, nearly 30 times deeper than Earth's. Oceans so deep they would create exotic forms of ice unlike anything found naturally on our planet. The Discovery team published their findings in the Astronomical Journal in August 2022, and the astronomical community took notice. Here was a planet that challenged our understanding of how worlds form and evolve. A water world unlike any in our solar system, yet potentially common throughout the galaxy. But before we dive deeper into what makes this planet so extraordinary, we need to understand what makes water worlds so rare in our cosmic backyard, and why finding one so close to Earth has profound implications for our search for life beyond our solar system. To appreciate just how unusual TOI 1452b is, we need to step back and look at our own cosmic neighborhood, the solar system. 8 major planets orbit our Sun. The inner 4, Mercury, Venus, Earth, and Mars, are rocky worlds with solid surfaces. The outer 4, Jupiter, Saturn, Uranus, and Neptune, are gas and ice giants, composed primarily of hydrogen, helium, and various ices, including water ice deep in their interiors. But none of them are water worlds in the sense that TOI 1452b appears to be. None have liquid water, making up a substantial fraction of their total mass. Earth, our blue marble, is often called a water world. From space, our planet's oceans dominate the view, covering 71% of the surface. But this is deceptive. If you could squeeze Earth like a sponge, very little water would come out. Our oceans account for just 0.02% of Earth's total mass. They're a thin veneer, averaging 3.7 kilometers deep, less than 0.1% of Earth's radius. So where are all the water worlds in our solar system? Shouldn't they be common? The answer lies in how our solar system formed, and it begins with what astronomers call the snow line or frost line. About 4.6 billion years ago, our solar system was just a swirling disk of gas and dust surrounding the newly forming sun. Close to the young star, temperatures were too high for water to condense into ice. It remained vapor. But beyond a certain distance, roughly where the asteroid belt now lies, temperatures dropped enough for water to freeze. This created a fundamental division in our solar system. Inside the snow line, planets formed primarily from rock and metal, the materials that could remain solid in the heat. Outside the snow line, water ice became an abundant building block, allowing the outer planets to accumulate massive amounts of water along with other materials. But here's the key point. Even though the outer planets contain enormous amounts of water, they also accumulated vast quantities of hydrogen and helium gas. These lightweight elements form thick atmospheres thousands of kilometers deep. Any water in these worlds is buried under crushing pressures, existing as exotic forms of ice or supercritical fluid, neither truly liquid nor gas. So despite having plenty of water, none of our solar system's planets evolved into the kind of world TOI 1452b appears to be, a super-Earth with deep global oceans of liquid water. But our solar system might be the exception rather than the rule. As we've discovered thousands of exoplanets orbiting other stars, we found a class of worlds that have no analog in our cosmic backyard. Planets with masses between Earth and Neptune, often called super-Earths or mini-Neptunes. These planets are the most common type we've found so far, yet our solar system has none. And many of them appear to have densities that suggest substantial water content. Take GJ 1214b, discovered in 2009. This planet, about 2.7 times Earth's radius, has a density that suggests it could be up to 50% water by mass. Or K218b, where in 2019, astronomers detected water vapor in its atmosphere, hinting at possible clouds or even oceans below. These discoveries have led some astronomers to propose that water worlds might be common throughout the galaxy, planets with global oceans hundreds, or even thousands of kilometers deep, resting atop rocky cores. But TOI 1452b stands out even among these unusual worlds. Its combination of size, mass, and proximity to Earth makes it an ideal target for further study. And its location in its star system places it in what astronomers call the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. This brings us to a profound question. If water worlds are common, and water is essential for life as we know it, could planets like TOI 1452b be the most habitable worlds in the galaxy? Before we can answer that, we need to understand exactly what makes TOI 1452b so special and why its very existence challenges our understanding of how planets form. TOI 1452b shouldn't exist, at least not according to our conventional understanding of planetary formation. To understand why, we need to examine the numbers more closely. This super-Earth has a radius about 1.67 times that of our planet, and a mass approximately 4.8 times greater. When astronomers calculate its density, mass divided by volume, they get a value that suggests up to 30% of this world could be water. This is where the problems begin. Planets form in the disks of gas and dust that surround young stars. In these protoplanetary disks, tiny dust grains collide and stick together, gradually building up larger and larger bodies. Eventually, some grow massive enough that their gravity attracts more material, and they become planetary embryos. The composition of these embryos depends largely on their location in the disk. Close to the star, where temperatures are high, only rock and metal can condense into solid form. Water and other volatiles remain as gases, unable to be incorporated into the growing planets. Further out, beyond the snow line we discussed earlier, water can freeze into ice, becoming a building block for planetary formation. This is why we expect water-rich worlds to form far from their stars, where ice is abundant during their birth. But TOI 1452b orbits very close to its star, completing a full orbit every 11.1 days. At this proximity, temperatures during formation should have been far too high for the planet to accumulate and retain such massive amounts of water. So how did it get there? How did a planet with oceans potentially 100 kilometers deep end up in an orbit where all that water should have boiled away long ago? This is where planetary migration enters our story. Astronomers now believe that planets rarely stay in the same orbits where they formed. Instead, they can migrate inward or outward due to interactions with the protoplanetary disk or with other planets. One possibility is that TOI 1452b 2b formed much further from its star, beyond the snow line where water ice was plentiful. There, it could have accumulated its substantial water content. Then, through migration processes, it gradually spiraled inward to its current location. But this explanation has problems too. As a water-rich planet migrates inward, the increasing heat from the star should cause it to lose much of its water through evaporation. The water molecules, energized by stellar radiation, would escape into space, leaving the planet drier than we observe TOI 1452b to be. Another possibility is that TOI 1452b was bombarded by water-rich asteroids and comets after its formation. These cosmic impacts could have delivered water to the planet's surface. We believe a similar process brought water to early Earth, but the sheer amount of water estimated to be on TOI 1452b makes this explanation problematic as well. The bombardment would need to be extraordinarily intense and prolonged to deliver water equivalent to 30% of the planet's mass. There's yet another complication. TOI 1452b orbits a red dwarf star, a type known for violent flares and intense radiation, especially when young. This stellar activity should strip away atmospheres and water from close orbiting planets. So not only would TOI 1452b need to acquire its massive water content through unlikely means, but it would also need to somehow protect this water from being lost to space over billions of years. The mystery deepens when we consider the planet's internal structure. With so much water, the pressure at the bottom of its oceans would be millions of times greater than at the deepest point in Earth's oceans. Under such extreme conditions, water behaves in ways that seem alien to our everyday experience. At these pressures, water forms exotic ice phases that remain solid even at temperatures that would boil water on Earth's surface. These high-pressure ices have different crystal structures than the ice in your freezer, with names like Ice 7, Ice 10, and Ice 11. The interior of TOI 1452b likely consists of layers, a rocky core surrounded by mantles of these exotic ices, topped perhaps by a global ocean of liquid water hundreds of kilometers deep. But maintaining such a structure over billions of years requires a delicate balance of heating and cooling processes. Too much internal heat, and the high-pressure ices melt, changing the planet's structure. Too little, and the entire water layer might freeze solid. All these factors make TOI 1452b seem like an impossible planet, a world that, according to our best theories, should not exist in the form we observe. Yet the data points strongly to its watery nature. This leaves us with an inescapable conclusion. Either our understanding of this particular planet is flawed, or our theories of planetary formation and evolution need serious revision. And this is what makes TOI 1452b so valuable to science. It's not just an interesting world, it's a challenge to our understanding. A cosmic puzzle that forces us to rethink our assumptions about how planets form, evolve, and maintain their compositions over cosmic timescales. In the next chapter, we'll explore the leading theories that might explain this impossible planet and what they tell us about the diversity of worlds in our galaxy. If we could slice TOI 1452b in half, like a cosmic apple, what would we see? How is a planet with 30% water by mass structured, and how does it differ from our familiar Earth? Let's start from the center and work our way out. At the heart of TOI 1452b likely lies a rocky core, similar in composition to Earth's interior: iron, nickel, silicates, and other heavy elements. But unlike Earth, where these materials make up the vast majority of our planet's mass, in TOI 1452b, they might account for only about 70% of the total. Surrounding this core would be something entirely unlike anything in Earth's interior: a mantle of water, not in the liquid form we're familiar with, but in exotic high-pressure phases. On Earth, we know water in three common states: solid ice, liquid water, and water vapor. But these are just the beginning of water's repertoire of forms. Under extreme pressure, water molecules arrange themselves into crystal structures vastly different from ordinary ice. At pressures above about 20,000 atmospheres, the kind of pressures found hundreds of kilometers deep in TOI 1452b, water transforms into what scientists call Ice 6 and Ice 7. These exotic ices remain solid even at temperatures that would boil liquid water on Earth's surface. Go deeper still, to pressures above 2 million atmospheres, and water becomes Ice 10, where the hydrogen atoms position themselves exactly between oxygen atoms, creating a symmetric crystal unlike any natural ice on Earth. These exotic ice layers would form a thick mantle around the rocky core of TOI 1452b, potentially hundreds of kilometers deep. Above this mantle of high-pressure ice would be a layer of liquid water, a global ocean potentially 100 kilometers deep or more. For comparison, the deepest point in Earth's oceans, the Challenger Deep in the Mariana Trench, reaches just 11 kilometers. The ocean on TOI 1452b could be 10 times deeper than our most extreme depths. The pressure gradient in such an ocean would be extraordinary. At the bottom, where liquid water meets the exotic ice mantle, pressures would reach hundreds of thousands of atmospheres. Even the toughest submarine we've ever built would be crushed like an aluminum can long before reaching such depths. Above this vast ocean would be an atmosphere, but what kind? This is where things get even more interesting. The atmosphere of TOI 1452b depends largely on its temperature, which in turn depends on how much energy it receives from its star. TOI 1452b orbits in what astronomers call the habitable zone of its red dwarf star, the region where temperatures might allow liquid water to exist on a planet's surface. But habitable zone is a deceptive term. It doesn't guarantee Earth-like conditions. Red dwarfs emit most of their energy as infrared radiation rather than visible light, creating a very different energy environment that our Sun provides. If TOI 1452b's surface temperature is similar to Earth's, its atmosphere might contain water vapor, carbon dioxide, and possibly nitrogen or other gases. But if it's significantly warmer, the planet could develop what scientists call a steam atmosphere, a thick envelope of water vapor creating intense greenhouse heating. In a steam atmosphere scenario, surface temperatures could soar to hundreds of degrees, making the planet more like Venus than Earth, despite all its water. The boundary between ocean and atmosphere would blur, with no clear shoreline, but rather a gradual transition from supercritical fluid to vapor. Alternatively, if the planet is cooler, much of its water could be locked in its ice mantle, with a thinner ocean above and a more moderate atmosphere. In this case, the surface might be more hospitable to life as we know it. What makes TOI 1452b particularly fascinating is that its structure would be fundamentally different from any planet in our solar system. It represents a class of world that planetary scientists have theorized about, but never observed up close, the true water world. In our solar system, we have rocky planets with thin veneers of water, like Earth. We have ice giants like Neptune, where water exists primarily as supercritical fluid mixed with other compounds deep in the interior. But we have no planets where water makes up a substantial fraction of the mass, while remaining distinct from a thick hydrogen-helium atmosphere. TOI 1452b fills this gap. It's what scientists sometimes call an ocean planet, a world where water is not just a surface feature, but a fundamental component of the planetary structure. The existence of such worlds has profound implications for our understanding of planetary diversity. It suggests that the galaxy contains types of planets with no analog in our solar system, worlds that evolved along entirely different paths than the 8 planets orbiting our Sun. But the structure of TOI 1452b raises another fascinating question. If this planet has oceans 30 times deeper than Earth's, could these vast waters harbor life? And if so, what kind of life could evolve in an environment so alien to our own? To answer these questions, we need to examine the conditions in these deep oceans and ask whether they could provide the necessary ingredients for life to emerge and thrive. When we search for life beyond Earth, we follow a simple principle: look for water. Every organism on our planet requires water to survive. It serves as the universal solvent, the medium in which the chemistry of life unfolds. By this measure, TOI 1452b should be a biological paradise, a world with more liquid water than dozens of Earths combined. But is water alone enough for life? And could life survive in the extreme conditions of this super-Earth's oceans? To answer these questions, we need to consider what makes Earth's oceans so conducive to life, and whether TOI 1452b's waters share these life-supporting qualities. On Earth, our oceans are more than just water. They contain dissolved minerals, salts, and gases that provide the chemical building blocks for life. They're illuminated by sunlight, which powers photosynthesis, a process that forms the base of most marine food webs. And they interact with land, creating diverse environments from tidal pools to deep-sea vents. TOI 1452b's oceans would be fundamentally different. For one thing, they might have no shoreline, no boundary between land and sea. If water makes up 30% of the planet's mass, it likely forms a continuous global ocean, covering the entire world. Without continents or islands, there would be no tidal pools, no estuaries, no shallow coastal waters. environments that played crucial roles in the evolution of life on Earth. Some scientists believe that life on our planet may have originated in these boundary zones where land and sea interact. But the absence of land doesn't rule out life. After all, some of Earth's most extreme environments harbor thriving ecosystems without any connection to the surface. Consider hydrothermal vents, fissures in the ocean floor where superheated water, rich in minerals and chemicals, billows into the cold, deep sea. These vents support complex ecosystems, powered not by sunlight, but by chemosynthesis, the process by which microbes extract energy from chemical reactions. TOI 1452b almost certainly has a hot rocky core beneath its water layers. Where this core meets the high-pressure ice or liquid water above, conditions might be similar to Earth's hydrothermal vents, creating environments where chemosynthetic life could potentially emerge. But there's a catch. On Earth, these deep ecosystems ultimately depend on oxygen and other compounds that originated at the surface through photosynthesis. Even if life could begin around hydrothermal vents on TOI 1452b, could it evolve into complex forms without this connection to a sunlit surface? The answer depends largely on what's happening at the top of those 100-kilometer deep oceans. If TOI 1452b has a thin, Earth-like atmosphere, sunlight could penetrate the upper layers of its oceans, allowing photosynthetic organisms to evolve. These organisms could produce oxygen and organic compounds that might eventually reach the deeper layers, creating a planet-wide ecosystem spanning from surface to depths. But if the planet has a fixed steam atmosphere, little sunlight would reach the water. In this case, life might be restricted to chemosynthetic forms clustered around geological features on the ocean floor. There's another factor to consider: the immense pressure in TOI 1452b's oceans. At depths of 100 kilometers, pressures would reach levels that no organism on Earth has ever adapted to. The deepest living fish in our oceans have been found at about 8 kilometers, where pressures reach about 800 times that at sea level. In TOI 1452b's deepest waters, pressures could be thousands of times greater. Could life evolve to withstand such crushing forces? Surprisingly, the answer might be yes. Laboratory experiments have shown that some microorganisms can survive pressures far beyond those found in Earth's oceans. Certain proteins and cellular structures actually become more stable under extreme pressure. The real challenge for life in TOI 1452b's oceans might not be pressure, but temperature. If the planet is too close to its star, or if its thick water layer creates too strong a greenhouse effect, the oceans could be too hot for complex molecules to form stable structures. Conversely, if the planet is too far from its star, or if its atmosphere doesn't trap enough heat, much of its water could freeze into exotic ice forms, leaving only a relatively thin liquid layer near the surface. The most favorable scenario for life would be a planet with the right balance, warm enough to maintain vast liquid oceans, but cool enough to allow complex chemistry to unfold. And there's one more wild card to consider: the nature of TOI 1452b's star. Red dwarf stars like TOI 1452 are known for their violent flares and intense radiation, especially when young. This radiation could strip away atmospheres and sterilize the surfaces of nearby planets. But water is an excellent radiation shield. Even if TOI 1452b's surface is regularly bathed in stellar flares, life could potentially find refuge in the depths, protected by kilometers of water above. In fact, the deep oceans of water worlds might be among the most stable environments in the galaxy, insulated from temperature extremes, protected from radiation, and potentially rich in the chemical ingredients needed for life. This raises an intriguing possibility. Could water worlds like TOI 1452 be more conducive to the emergence of life than Earth-like planets? Could the most common habitable worlds in the galaxy be not the rocky planets with thin water layers that we've been focusing on, but rather these ocean giants with their vast, protected depths? If so, we might need to rethink our approach to the search for extraterrestrial life. Instead of looking for the signatures of Earth-like atmospheres, perhaps we should be searching for the unique characteristics of these water worlds. Planets where life might thrive in, conditions utterly unlike those on our home world. But before we can answer these questions, we need to understand how common planets like TOI 1452b might be in our galaxy. Are they rare oddities, or do they represent a major class of worlds waiting to be discovered? TOI 1452b is not alone. As our exoplanet detection methods have improved, astronomers have discovered a growing population of worlds that might share its watery nature. Consider GJ1214b, one of the first potential water worlds identified. Discovered in 2009, this planet orbits a red dwarf star about 48 light-years from Earth, with a radius about 2.7 times that of Earth and a mass about 6.5 times greater. Its density suggests it could be composed of up to 50% water by mass, even more than TOI 1452b. Or take K218b, a planet about 124 light-years away. In 2019, astronomers detected water vapor in its atmosphere, the first such detection in the habitable zone of another star. While K218b is larger than TOI 1452b, with a radius about 2.6 times Earth's, its discovery reinforced the idea that water-rich worlds might be common in our galaxy. More recently, the TRAPPIST-1 system has captured astronomers' attention. This system contains 7 Earth-sized planets, orbiting a tiny red dwarf star about 40 light-years away. Based on their densities, several of these worlds could contain significant amounts of water, perhaps as much as 5% to 10% of their mass. These discoveries suggest that water worlds might form a substantial population among the exoplanets in our galaxy. But just how common are they? To answer this question, astronomers have turned to statistical analyses of the thousands of exoplanets discovered so far. These studies reveal something surprising: planets with radii between 1.5 and 2.5 times that of Earth. The size range that includes TOI 1452b are among the most common in our galaxy. These super-Earths, or mini-Neptunes, appear to be everywhere, orbiting stars of all types. Yet our solar system has none. This suggests that our cosmic neighborhood might be unusual in its planetary architecture. Even more intriguing, many of these super-Earths have densities too low to be composed entirely of rock and metal. They must contain substantial amounts of lighter materials, and water is a prime candidate. A 2019 study led by Li Zheng of Harvard University suggested that up to 35% of all known exoplanets larger than Earth might be water worlds, with water making up more than 50% of their mass. If this estimate is correct, water worlds could be among the most common potentially habitable planets in the galaxy, far more numerous than Earth-like rocky planets with thin oceans. But there's an important caveat. Most of the potential water worlds discovered so far orbit red dwarf stars, the smallest, coolest, and most common type of star in our galaxy. These stars present unique challenges for habitability. Red dwarfs emit most of their energy as infrared radiation rather than visible light. They're prone to violent flares that can strip away planetary atmospheres. And planets in their habitable zones are often tidally locked, with one side perpetually facing the star while the other remains in eternal night. These factors could make water worlds around red dwarfs very different environments than Earth, even if they have the right temperatures for liquid water. The constant radiation might sterilize their surfaces. The tidal locking could create extreme temperature differences between their day and night sides. But again, the deep oceans of these worlds might provide refuge. Water absorbs infrared radiation effectively, potentially creating a more stable temperature environment below the surface. And the sheer depth of these oceans could protect life from stellar flares and radiation. In fact, some astrobiologists have suggested that the deep oceans of water worlds might be among the most stable and protected environments in the galaxy. Cosmic oases where life could emerge and thrive, sheltered from the harsh conditions above. If this is true, then the most common habitable environments in our galaxy might not resemble Earth's surface at all. They might be more like the deep oceans of TOI 1452b, vast, dark realms where pressure creates exotic conditions unlike anything in our everyday experience. This possibility forces us to expand our conception of habitability. When we search for life beyond Earth, we often look for planets that resemble our own rocky worlds with thin atmospheres, moderate temperatures, and surface water. But what if the majority of life in the universe exists in environments utterly unlike our familiar surface world? What if the typical abode of life is not a shallow ocean lapping against rocky shores under a blue sky, but rather a deep, pressurized realm where sunlight never penetrates, where water exists in exotic forms, and where organisms have evolved under conditions that would crush any surface dweller? This is the tantalizing possibility raised by planets like TOI 1452b. They suggest that our galaxy might be teeming with habitable worlds, just not the kind we've been focusing on in our search for life beyond Earth. But to confirm this possibility, we need better observations. We need to determine the true composition of these potential water worlds, to measure their atmospheres, to understand their internal structures. And for that, we need the next generation of telescopes and instruments. In the coming decade, new observatories like the James Webb Space Telescope and ground-based extremely large telescopes will give us unprecedented views of exoplanets. They'll allow us to analyze the atmospheres of worlds like TOI 1452b in detail, searching for the chemical signatures that might reveal the presence of life. Until then, planets like TOI 1452b remain tantalizing mysteries, worlds that challenge our understanding of planetary formation, expand our conception of habitability, and hint at the incredible diversity of environments that might harbor life in our galaxy. But the story of TOI 1452b isn't just about a distant world. It's also about how we came to discover it, and what that tells us about our own technological evolution. The discovery of TOI 1452b represents a triumph of modern astronomy, the ability to detect and characterize a planet 100 light-years away, a world so distant that even our most powerful telescopes can't directly image it. How did astronomers accomplish this feat? The story involves ingenious methods, powerful instruments, and international collaboration. The first hint of TOI 1452b's existence came from NASA's Transiting Exoplanet Survey Satellite, or TESS, launched in April 2018. Unlike previous planet-hunting missions that focused on small patches of sky, TESS was designed to survey nearly the entire celestial sphere, focusing on the brightest nearby stars. TESS uses the transit method to detect planets. It watches stars continuously, measuring their brightness with extreme precision. When a planet passes in front of its star, an event called a transit, it blocks a tiny fraction of the star's light. This creates a small but detectable dip in the star's brightness. The amount of dimming tells astronomers about the planet's size. The bigger the planet, the more starlight it blocks. The timing of these dips reveals the planet's orbital period, how long it takes to complete one orbit around its star. In the data from TOI 1452, a red dwarf star in the constellation Draco, TESS detected periodic dimming that occurred every 11.1 days. The depth of these transits suggested a planet about 1.67 times the radius of Earth, placing it in the super-Earth category. But size alone doesn't tell us much about a planet's nature. To determine whether TOI 1452b was a rocky world like Earth or something more exotic, astronomers needed to know its mass. And for that, they needed a different technique. Enter the radial velocity method. When a planet orbits a star, it exerts a gravitational pull on the star, causing the star to wobble slightly. This wobble creates tiny shifts in the star's spectrum, the rainbow of light that astronomers analyze to determine a star's composition, temperature, and motion. When the star moves toward Earth, its spectral lines shift slightly toward the blue end of the spectrum. When it moves away, they shift toward the red end. By measuring these shifts, astronomers can determine how much the star is wobbling, which in turn reveals the mass of the planet causing the wobble. For TOI 1452b, this follow-up work was conducted by a team led by Charles Cadillo, a PhD student at the Université de Montréal. They used the SPIRO spectrograph on the Canada-France-Hawaii telescope in Hawaii and the Harpsen instrument on the Telescopio Nazionale Galileo in the Canary Islands. These observations revealed that TOI 1452b has a mass approximately 4.8 times that of Earth. Combined with its radius of 1.67 Earth radii, this gave astronomers the planet's density, about 5.6 grams per cubic centimeter. This is where the detective work really began. A planet's density provides crucial clues about its composition. Rocky planets like Earth are dense. Our planet's average density is about 5.5 grams per cubic centimeter. Gas giants like Jupiter are much less dense, about 1.3 grams per cubic centimeter. At first glance, TOI 1452b's density seems similar to Earth's, suggesting it might be a rocky world. But there's a complication. Larger planets naturally compress their materials due to stronger gravity. A super-Earth made of the same materials as our planet should be denser than Earth, not slightly less dense. This discrepancy led astronomers to conclude that TOI 1452b must contain substantial amounts of materials lighter than rock, and the most likely candidate is water. Using models of planetary structure, the research team calculated that water could make up to 30% of TOI 1452b's total mass, an extraordinary amount compared to Earth's meager 0.1%. But even with these sophisticated methods, there's still uncertainty. The mass and radius measurements have margins of error. The models of planetary structure involve assumptions. TOI 1452b might be a water world, but it could also be a rocky planet with a thick hydrogen-rich atmosphere, or something else entirely. To resolve these uncertainties, astronomers need more data, particularly spectroscopic observations of the planet's atmosphere. By analyzing which wavelengths of light are absorbed as starlight passes through the planet's atmosphere during transit, they can determine its composition. This is where the James Webb Space Telescope comes in. Launched in December 2021, Webb represents a quantum leap in our ability to study exoplanet atmospheres. Its infrared instruments are perfectly suited to observing planets around red dwarf stars like TOI 1452. In fact, the Discovery team specifically noted that TOI 1452b is an excellent target for Webb observations. Its relatively large size, its proximity to Earth just 100 light years, and its orbit around a bright star make it ideal for atmospheric characterization. If Webb confirms the presence of water vapor in TOI 1452b's atmosphere, it would strengthen the case for this world being a true water planet. It might even detect other compounds that could hint at the presence of life. But even without these future observations, the discovery of TOI 1452b2 represents a remarkable achievement. Just 3 decades ago, we didn't know for certain if planets existed around other stars. Now, we're not only finding them by the thousands, but determining their compositions and contemplating their habitability. This progress reflects the extraordinary advances in astronomical instrumentation and techniques. Tests can detect changes in stellar brightness as small as 50 parts per million, equivalent to noticing when a single light bulb dims among 20,000. Spectrographs like SPI-RO can measure stellar wobbles caused by planets, revealing their masses even when the planets themselves remain invisible. These capabilities would have seemed like science fiction to astronomers of previous generations. Yet today, they allow us to discover and characterize worlds like TOI 1452b, planets so distant that their light takes a century to reach us. The story of how we discovered TOI 1452b also highlights the international, collaborative nature of modern astronomy. The initial detection came from a NASA satellite. The follow-up observations involved telescopes in Hawaii and the Canary Islands. The research team included scientists from Canada, France, Brazil, and the United States. This collaboration reflects a fundamental truth about astronomy: that cosmos belongs to all humanity, and understanding it requires us to work together across national boundaries. As we continue to refine our methods and develop more powerful instruments, we'll discover more worlds like TOI 1452b, planets that challenge our understanding and expand our cosmic perspective. Each discovery brings us closer to answering one of humanity's most profound questions: are we alone in the universe? But the significance of TOI 1452b goes beyond its potential habitability. This world also offers insights into the fundamental processes that shape planetary systems, processes that might have operated very differently around TOI 1452 than they did in our solar system. The existence of TOI 1452b presents a cosmic puzzle. How does a planet end up with oceans 30 times deeper than Earth's? How can water make up 30% of a world's mass when it accounts for less than 0.1% of our own planet? To solve this puzzle, we need to understand how planets form and how this process might differ around stars like TOI 1452 compared to our Sun. The basic story of planetary formation begins with a cloud of gas and dust, the raw materials left over from the birth of a star. This material forms a disk around the young star, and within this disk, tiny dust grains begin to collide and stick together. Over time, these aggregations grow from microscopic particles to pebbles, from pebbles to boulders, and eventually to planetary embryos, bodies large enough that their gravity attracts more material, accelerating their growth. The composition of these growing planets depends largely on their location in the disk. Close to the star, temperatures are high, and only materials with high melting points, primarily rock and metal, can condense into solid form. Water and other volatiles remain as gases, unable to be incorporated into the growing planets. Further from the star, beyond what astronomers call the snow line or frost line, temperatures drop enough for water to freeze into ice. Here, growing planets can accumulate substantial amounts of water along with rock and metal. In our solar system, this process produced a clear division. Rocky planets like Earth formed inside the snow line, while the gas and ice giants formed beyond it. But TOI 1452b doesn't fit neatly into either category. It orbits very close to its star, completing a circuit every 11.1 days, yet appears to contain enormous amounts of water. So how did it get there? Astronomers have proposed several possible formation pathways for water worlds like TOI 1452b. One possibility is that the planet formed much further from its star, beyond the snow line where water ice was abundant. There, it accumulated its substantial water content. Then, through a process called orbital migration, it gradually spiraled inward to its current location. Migration can occur through several mechanisms. A planet can interact with the gas in the protoplanetary disk, losing energy and spiraling inward. It can be influenced by gravitational interactions with other planets in the system, or it could be affected by tides raised on the star by the planet's gravity. This scenario, formation beyond the snow line followed by inward migration, could explain TOI 1452b's watery nature despite its close orbit. But it raises another question. Why didn't the water evaporate as the planet moved closer to its star? When a water-rich planet migrates inward, the increasing heat from the star should cause it to lose much of its water through a process called hydrodynamic escape. Water molecules in the upper atmosphere, energized by stellar radiation, gain enough energy to escape the planet's gravity. This process has shaped the evolution of planets in our solar system. Venus, for instance, may once have had oceans similar to Earth's, but its proximity to the Sun led to a runaway greenhouse effect and the eventual loss of its water. So how did TOI 1452b retain its massive water content despite orbiting so close to its star? The answer might lie in the planet's size and the nature of its star. With a mass 4.8 times that of Earth, TOI 1452b has a stronger gravitational pull, making it harder for water molecules to escape. Additionally, if the planet formed with even more water than it has today, it could have lost a significant fraction while still retaining enough to make up 30% of its current mass. The nature of TOI 1452, a red dwarf star, also plays a role. Red dwarfs are smaller, cooler, and dimmer than our Sun. A planet orbiting in the habitable zone of a red dwarf receives less total energy than Earth does from the Sun, potentially reducing the rate of atmospheric escape. But there's a complication. Red dwarfs are known for their violent flares and intense ultraviolet radiation, especially when young. This radiation can strip away planetary atmospheres and water over time. This presents another puzzle. How did TOI 1452b protect its water from being lost to space over billions of years of exposure to stellar flares? One possibility is that the planet has a strong magnetic field that shields its atmosphere from stellar radiation. Earth's magnetic field performs a similar protective function, deflecting charged particles from the Sun that would otherwise strip away our atmosphere. Another possibility is that TOI 1452b's water is mostly contained in its interior rather than on its surface. Water incorporated into a planet's mantle or locked in high-pressure ice phases would be protected from stellar radiation. There's yet another formation scenario to consider. Rather than forming beyond the snow line and migrating inward, TOI 1452b might have formed roughly where it is now, but through a different process than the planets in our solar system. Recent research suggests that planets forming around red dwarf stars might incorporate water through a process called pebble accretion. In this scenario, small ice-rich pebbles from beyond the snow line drift inward to the protoplanetary disk. As they pass the growing planet, they're captured by its gravity, delivering water directly to a world forming in the inner system. This process might be particularly efficient around red dwarf stars, where the snow line is much closer to the star than in our solar system due to the star's lower temperature. There's one more possibility that's more speculative, but fascinating to consider. What if TOI 1452b didn't form in its current system at all? What if it formed around a different star and was later captured by TOI 1452? Such planetary capture events are thought to be rare, but not impossible. They could occur when two star systems pass close to each other, or in dense stellar clusters where stars form in close proximity. If TOI 1452b originated in a different environment, perhaps around a star where water-rich planets could form and remain stable, and was later captured by its current star, it might explain its unusual properties. While this scenario is less likely than the others, it reminds us that planetary systems are not static. They evolve over billions of years, shaped by processes we're only beginning to understand. Whatever its formation pathway, TOI 1452b represents a type of world that has no analog in our solar system. A super-Earth water is a major component of its mass. Its existence suggests that planetary formation and evolution can follow diverse paths, producing worlds far different from the 8 planets that orbit our Sun. As we discover more planets like TOI 1452b, we'll refine our understanding of these formation pathways. We'll learn which scenarios are common and which are rare, and we'll gain insight into the processes that shape planetary systems throughout our galaxy. But the significance of TOI 1452b goes beyond questions of formation. This world also offers a glimpse into a possible future for our own planet, a future where rising sea levels reshape Earth's surface and human civilization. When astronomers look at TOI 1452b, they see a world utterly unlike our own. A planet where oceans plunge to depths of 100 kilometers or more, where water makes up nearly a third of the total mass. But in this alien world, some scientists see something else, a possible glimpse of Earth's distant future. Our planet is changing. Human activities, particularly the burning of fossil fuels, have increased atmospheric carbon dioxide levels, trapping heat and warming the planet. One of the most visible consequences of this warming is rising sea levels. As ocean waters warm, they expand. As ice sheets and glaciers melt, they add more water to the oceans. Together, these processes have raised global sea levels by about 20 centimeters since 1900, and the rate is accelerating. Current projections suggest that by 2100, sea levels could rise by another meter or more, depending on how quickly we reduce greenhouse gas emissions. This would inundate coastal cities, displace millions of people, and redraw Earth's coastlines. But what about the longer term? What might happen to Earth's oceans over thousands or millions of years if warming continues? Earth contains vast stores of ice, primarily in Antarctica and Greenland. The Antarctic ice sheet alone contains enough water to raise global sea levels by about 58 meters if it were to melt completely. Add Greenland's ice sheet and mountain glaciers worldwide, and you're looking at about 70 meters of potential sea level rise. This wouldn't transform Earth into another TOI 1452b. Our oceans would still make up only a tiny fraction of the planet's mass, but it would dramatically reshape our world's geography. Many of today's coastal cities would be deep underwater. New shorelines would form far inland. Islands and peninsulas would disappear beneath the waves. Of course, the complete melting of Earth's ice sheets would take thousands of years even under extreme warming scenarios. And there are negative feedbacks in Earth's climate system that would likely prevent such an extreme outcome. But TOI 1452b reminds us that planets can take many forms. The thin layer of water that covers much of Earth's surface, the oceans that seem so vast from our perspective, is just one possible configuration. Worlds can exist where water is not just a surface feature, but a fundamental component of planetary structure. This perspective helps us appreciate the delicate balance that makes Earth habitable for complex life. Our planet has just enough water to support diverse ecosystems, from deep oceans to shallow seas, from rivers and lakes to wetlands and rainforests. But not so much water that the entire surface is submerged beneath a global ocean hundreds of kilometers deep. TOI 1452b also offers a humbling reminder of our planet's cosmic context. Earth is just one world among billions in our galaxy, a small rocky planet with a thin veneer of water orbiting an average star. There are worlds out there far wetter than ours, just as there are worlds far drier. This cosmic perspective doesn't diminish the urgency of it. Addressing climate change and protecting Earth's unique environments. If anything, it enhances it. If planets like TOI 1452b are common, then worlds like Earth, with the perfect balance of land and water to support complex surface life, might be relatively rare and precious. But TOI 1452b also expands our imagination about what constitutes a habitable world. Perhaps life doesn't require the specific balance of land and water that we have on Earth. Perhaps it can thrive in the deep, oceans of water worlds, evolving forms and adaptations utterly unlike the life we know. This brings us to one of the most profound questions raised by the discovery of TOI 1452b. If life exists on this distant water world, what might it be like? How would organisms adapt to the extreme conditions of pressure, darkness, and isolation that would characterize its deep oceans? To answer these questions, we need to look to the most extreme environments on our own planet, the places where life has evolved to survive conditions that would kill most organisms. And we need to consider how these adaptations might be taken to even greater extremes on a world like TOI 1452b. The deepest parts of Earth's oceans are among the most extreme environments on our planet. In the Mariana Trench, nearly 11 kilometers below the surface, pressures reach over 1,000 times that at sea level. No sunlight penetrates these depths. Temperatures hover just above freezing. Yet even here, life thrives. Deep-sea creatures have evolved remarkable adaptations to survive in this harsh realm. Some fish have specialized proteins that prevent their cells from being crushed under extreme pressure. Many organisms have developed bioluminescence, the ability to produce their own light through chemical reactions, to communicate, attract prey, or find mates in the darkness. At hydrothermal vents on the ocean floor, entire ecosystems exist based not on sunlight, but on chemosynthesis, the process by which microbes extract energy from chemical reactions involving hydrogen sulfide and other compounds released from Earth's interior. These adaptations offer clues about how life might evolve on a water world like TOI 1452b. But the conditions on this distant planet would be far more extreme than anything on Earth. In TOI 1452b's oceans, pressures could reach millions of atmospheres in the deepest layers. Temperatures would vary dramatically with depth, perhaps comfortable near the surface, but increasing to hundreds of degrees where the liquid ocean meets the high-pressure ice mantle below. What kind of life could evolve in such an environment? At the most basic level, organisms on TOI 1452b would need cellular structures capable of withstanding enormous pressures. On Earth, deep-sea organisms have evolved proteins and cell membranes that remain functional under pressure. On TOI 1452b, these adaptations would need to be taken to extremes beyond anything in Earth's oceans. One possibility is that life might evolve to incorporate high-pressure ice into its structures. These exotic ice phases, stable at pressures found deep in TOI 1452b's oceans, have different properties than ordinary ice. They're denser than liquid water and remain solid even at temperatures that would boil water on Earth's surface. Organisms might use these ice crystals as structural elements, similar to how some Earth organisms use minerals to form shells or skeletons. Such ice-based life would be utterly alien to our experience. Creatures with bodies partially composed of exotic water, crystals that would instantly melt if brought to Earth's surface. Another adaptation would involve energy sources. In the perpetual darkness of TOI 1452b's deep oceans, photosynthesis as we know it would be impossible. Life would need alternative energy sources. One possibility is chemosynthesis, similar to what occurs around Earth's hydrothermal vents. If TOI 1452b has active geology, and its size suggests it would, then its ocean floor might feature vents where energy-rich chemicals bubble up from the planet's interior. These vents could create oases of life in the deep ocean, with microorganisms extracting energy from chemical reactions and forming the base of complex food webs. Larger organisms might evolve to harvest these microbes or prey on other creatures drawn to the vents. Another potential energy source is thermal gradients. If TOI 1452b's oceans feature significant temperature differences between layers, organisms might evolve to extract energy from this thermal differential, similar to how heat engines work. Communication would present another challenge. In Earth's oceans, many creatures use sound, which travels efficiently through water. On TOI 1452b, sound might be even more important. potentially leading to the evolution of sophisticated acoustic organs and complex languages of clicks, whistles, and songs. Bioluminescence might also play a crucial role. On Earth, approximately 90% of deep-sea creatures can produce their own light. On TOI 1452b, this percentage might be even higher, with organisms evolving even more sophisticated light-producing organs to communicate, attract prey, or find mates in the darkness. The planet's gravity, about twice that of Earth based on its mass, would also shape the evolution of life. Creatures would likely be more compact and muscular than their Earth counterparts, with reinforced skeletons or support structures to counter the increased gravitational pull. But perhaps the most fascinating possibility is that life on TOI 1452b might organize itself into distinct layers, each adapted to the specific conditions at different ocean depths. Near the surface, where conditions might be most Earth-like, organisms could evolve to harness whatever light penetrates from the star above. These surface dwellers might resemble the plankton and fish of Earth's upper oceans, though adapted to TOI 1452b's higher gravity and potentially different atmospheric composition. In the middle layers, where pressure increases but temperatures remain moderate, we might find the ocean's most diverse ecosystems. Here, predators and prey might engage in evolutionary arms races, developing sophisticated senses, propulsion systems, and defensive mechanisms. And in the deepest layers, where pressure reaches extremes and the ocean meets the high-pressure ice mantle, we might find the most alien life forms, organisms that thrive under conditions that would crush any Earth creature, perhaps incorporating exotic ice phases into their very bodies. These deep dwellers might never rise to the upper ocean, just as abyssal creatures on Earth rarely venture to the surface. They might evolve in isolation, developing forms and adaptations utterly unlike anything in the upper layers. This layered biosphere could create a planet with multiple distinct evolutionary domains, almost like having several alien worlds stacked on top of each other within the same ocean. But there's another intriguing possibility to consider. What if life on TOI 1452b isn't confined to individual organisms as we understand them on Earth? What if the extreme conditions have led to the evolution of collective organisms, vast networks of interconnected cells or entities that function as a single system? On Earth, we see hints of this in colonial organisms like Portuguese man-o'-wars, which appear to be single creatures, but are actually colonies of specialized individuals working together. Or mycelial networks of fungi, which can span vast areas underground, connecting trees and plants in what some scientists call the Wood Wide Web. In the extreme environment of TOI 1452b's oceans, such collective organizations might be taken to new levels. Perhaps vast networks of interconnected organisms span different ocean layers, sharing resources and information across pressure and temperature gradients that no single organism could traverse. These networks might function as distributed intelligence systems, not centralized brains as we understand them, but consciousness emerging from the interactions of countless specialized nodes spread throughout the ocean. Such life would be fundamentally different from anything on Earth, not just in form, but in the very organization of life and mind. It would challenge our definitions of what constitutes an individual organism and what constitutes intelligence. Of course, all of this is speculation. We have no direct evidence that life exists on TOI 1452b or any other exoplanet. But by combining our understanding of extreme life on Earth with the physical conditions we can infer on distant worlds, we can imagine possibilities that expand our conception of what life might be. And this is one of the most valuable aspects of exoplanet research. It forces us to question our assumptions about life, to consider possibilities beyond our Earth-centric experience. It reminds us that life, if it exists elsewhere in the universe, might take forms we can barely imagine. But to move beyond speculation, we need more data. We need to observe TOI 1452b and similar worlds in greater detail, to analyze their atmospheres for potential biosignatures, to understand their surface conditions and internal structures. And for that, we need the next generation of astronomical instruments, tools that will allow us to see these distant worlds not just as points of light or statistical data, but as real places with atmospheres, oceans, and perhaps even biospheres. TOI 1452b remains largely a world of numbers and models, a planet defined by its radius, mass, density, and orbit. But astronomers are working to transform it from an abstract data point into a real world with known characteristics and conditions. The key to this transformation lies in spectroscopy, the analysis of light to determine the composition of distant objects. When a planet transits its star, a small fraction of the starlight passes through the planet's atmosphere. Different molecules in the atmosphere absorb specific wavelengths of this light, creating a pattern of absorption lines in the spectrum, a chemical fingerprint that reveals the atmosphere's composition. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in our ability to perform this kind of analysis. With its large mirror and advanced infrared instruments, Webb can detect the faint signals of exoplanet atmospheres with unprecedented precision. TOI 1452b is an ideal target for Webb observations. Its relatively large size, its proximity to Earth, just 100 light-years, and its orbit around a bright star make it accessible to Webb's instruments. Most importantly, if TOI 1452b has a substantial atmosphere, Webb should be able to detect it and determine its major components. What might these observations reveal? If TOI 1452b is indeed a water world, Webb might detect water vapor in its atmosphere, a finding that would strengthen the case for oceans below. It might also detect other compounds, such as carbon dioxide, methane, or oxygen, which could provide clues about the planet's climate and potential habitability. The presence of certain combinations of gases, particularly oxygen and methane together, might even hint at the presence of life. These gases react with each other relatively quickly, so finding them together suggests they're being continuously replenished, possibly by biological processes. But Webb is just the beginning. Future observatories, both in space and on the ground, will provide even more detailed views of worlds like TOI 1452b. The Habitable Worlds Observatory, currently in the planning stages, would be specifically designed to directly image Earth-like exoplanets and analyze their atmospheres for signs of life. Unlike Webb, which primarily observes planets as they transit their stars, this observatory would use advanced coronagrus to block out the light of the host star, allowing direct observation of the planet itself. On the ground, extremely large telescopes with mirrors 30 meters or more in diameter are under construction in Chile and Hawaii. These behemoths will collect enough light to study exoplanet atmospheres in unprecedented detail, potentially revealing weather patterns, seasonal changes, and even surface features. These future observations might transform TOI 1452b from a mysterious water world into a well-characterized planet with known atmospheric composition, surface temperature, and perhaps even insights into its internal structure. But even with these advanced instruments, certain aspects of TOI 1452b will remain beyond our reach, at least for the foreseeable future. We won't be able to directly observe its oceans or any life that might dwell within them. We won't be able to measure the exact depth of its waters or confirm the presence of exotic ice phases in its interior. For these details, we would need to send a probe, a journey that remains far beyond our current technological capabilities. At 100 light years, TOI 1452b is about 600 trillion miles from Earth. Our fastest spacecraft, traveling at about 40,000 miles per hour, would take over 1.7 million years to reach it. Even communications are limited by the speed of light. Any signal we send to TOI 1452b would take 100 years to arrive, and another 100 years for the response to return to Earth. This means that even if we could somehow observe the planet in real time, we would be seeing it as it was a century ago. These limitations remind us of the vast scales of our galaxy and the challenges of interstellar exploration. For the foreseeable future, our understanding of TOI 1452b and similar worlds will come from remote observations, powerful telescopes that capture the faint light from these distant planets and extract from it the secrets of their nature. But even these limited observations have profound value. They allow us to test our models of planetary formation and evolution. They expand our understanding of the diversity of worlds in our galaxy. And they help us place our own planet in cosmic context. One world among billions, with its own unique history and characteristics. As we continue to observe TOI 1452b and discover more planets like it, we're building a census of our galactic neighborhood, a catalog of the different types of worlds that exist around nearby stars. This census will help us answer fundamental questions about how common Earth-like planets are, how diverse planetary systems can be, and ultimately, how likely it is that life exists beyond our solar system. But the significance of TOI 1452b goes beyond scientific curiosity. This distant water world also captures our imagination, inviting us to contemplate what it would be like to visit or even live on a planet so different from our own. Imagine for a moment that we could overcome the vast distances of space and time. Imagine that we could send a probe to TOI 1452b or even visit it ourselves. What would we experience on this distant water world? Our journey would begin 100 light years from Earth, approaching a small red star, TOI 1452. Unlike our yellow sun, this star would appear orange-red, emitting most of its energy as infrared radiation rather than visible light. Orbiting this star, we would find our destination, TOI 1452b, a planet about 1.67 times the radius of Earth. From space, it might appear as a deep blue sphere, its surface covered entirely by water, with no continents or islands to break the endless ocean. As our spacecraft entered the planet's atmosphere, we would begin to feel the effects of its gravity, about twice that of Earth based on its mass. This increased gravitational pull would make movement more difficult, requiring more energy for every action. The atmosphere itself would likely contain substantial water vapor, perhaps creating a perpetual mist or fog above the ocean surface. Depending on the planet's temperature, there might be constant cloud cover, with storms far more intense than those on Earth, due to the planet's stronger gravity and the abundance of water. Landing on TOI 1452b would mean landing on water. There would be no solid ground to set foot on. Our spacecraft would need to float or hover above the endless ocean, or perhaps deploy submersibles to explore beneath the waves. At the surface, conditions might be somewhat familiar. Liquid water, temperatures potentially similar to Earth's, if the planet is indeed in the habitable zone of its star. But the sky would look alien. The red dwarf star would appear larger in the sky than our sun does on Earth, but dimmer and redder, casting an eerie light over the waters. If TOI 1452b is tidally locked to its star, with one side always facing the star while the other remains in perpetual darkness, then the planet's appearance would be even more dramatic. The day side might feature a vast, warm ocean under the constant glow of the red star. The night side would be dark and potentially much colder, perhaps even frozen at the surface. Between these extremes would be a terminator zone, the boundary between day and night, where fierce winds might blow constantly as air moves between the heated day side and the cooler night side. But the true alien nature of TOI 1452b would become apparent as we descended beneath the waves. Unlike Earth's oceans, which reach a maximum depth of about 11 kilometers, the oceans of this water world could extend downward for 100 kilometers or more. As we descended, pressure would increase dramatically, far beyond anything experienced in Earth's oceans. At a depth of just 10 kilometers, similar to the Mariana Trench, pressures would already reach about 1,000 atmospheres. But our submersible would need to withstand far greater pressures to explore the true depths of TOI 1452b's oceans. Light from the star above would fade quickly. By about 1 kilometer down, similar to the depth where light disappears in Earth's clearest oceans, we would be in perpetual darkness, with only our vessel's lights illuminating the alien waters. What might we see in those lights? If life exists on TOI 1452b, it might be most abundant near the surface, where energy from the star is available. These upper ocean organisms might resemble Earth's marine life in basic form, perhaps streamlined swimmers or drifting plankton-like creatures, though adapted to the planet's higher gravity and potentially different chemical environment. As we descended deeper, we might encounter more exotic life forms, creatures adapted to the increasing pressure and total darkness. They might use bioluminescence extensively, creating displays of living light more spectacular than anything in Earth's deep oceans. Deeper still, where pressures reach levels that would crush any Earth organism, we might find the most alien life of all, perhaps beings that incorporate high-pressure ice into their structures, or organisms that extract energy from the thermal gradient between different ocean layers. But the most dramatic sight would come if we could somehow descend all the way to the bottom of the ocean, where liquid water meets the high-pressure ice mantle. Here, at depths of perhaps 100 kilometers, we would find not a rocky seafloor as on Earth, but a solid boundary of exotic ice. Ice 7 or Ice 10, forms that remain solid even at temperatures that would boil water on Earth's surface. This boundary would mark the limit of the liquid ocean. Beyond it would be layers of increasingly exotic ice phases, eventually transitioning to the rocky core of the planet, hundreds of kilometers deeper still. Of course, no human-made submersible could realistically reach such depths. The pressures would be millions of times greater than at Earth's surface, far beyond the capabilities of any materials we can currently manufacture. This highlights a sobering reality about water worlds like TOI 1452b. Even if we could somehow travel the 100 light-years to reach them, much of their nature would remain inaccessible to direct exploration. The vast majority of such a planet's volume would be under pressures so extreme that they would crush any probe we could build with foreseeable technology. In this sense, water worlds present an exploration challenge even more daunting than gas giants like Jupiter. At least with gas giants, we can observe their atmospheric dynamics from orbit. But the depths of a water world would remain hidden, their secrets protected by layers of ocean and exotic ice. This inaccessibility adds to the mystery and allure of planets like TOI 1452b. They represent not just distant worlds, but realms of extreme conditions that we can study only indirectly, through models and remote observations. Yet even this limited understanding has value. It expands our conception of what planets can be. It challenges us to imagine environments utterly unlike our familiar Earth. And it reminds us of the incredible diversity of worlds that likely exist throughout our galaxy. In the end, TOI 1452b and planets like it represent both the triumph and the limitation of modern astronomy. We can detect these distant worlds, measure their basic properties, and even make educated guesses about their composition and structure. But much about them remains beyond our reach, at least for now. Perhaps future generations, with technologies we can barely imagine, will find ways to explore the depths of water worlds directly. Perhaps they will develop materials that can withstand the crushing pressures, or send robotic emissaries that can transmit data back across the light years. Until then, planets like TOI 1452b will remain tantalizing mysteries, worlds we can study from afar but never fully know. And in that mystery lies much of their appeal. They remind us that the universe is not just stranger than we imagine, but stranger than we can imagine. The discovery of TOI 1452b and other potential water worlds has profound implications that extend far beyond astronomy. These distant planets offer a new perspective on our own world and our place in the cosmos. First, they remind us of the incredible diversity of planets in our galaxy. For centuries, our understanding of what planets could be was limited to the 8 worlds of our solar system, from rocky Mercury to gaseous Neptune. But exoplanet discoveries have revealed a much richer tapestry. Hot Jupiters orbiting closer to their stars than Mercury, super-Earths and mini-Neptunes with no analog in our system, and now water worlds with oceans that might comprise a substantial fraction of their mass. This diversity suggests that planetary formation is a far more varied process than we once thought. Planets can form and evolve along many different pathways, producing worlds with compositions and structures utterly unlike those in our solar system. Second, water worlds like TOI 1452b challenge our assumptions about habitability. For decades, astrobiologists have focused on finding planets similar to Earth, rocky worlds with thin atmospheres and surface water. The Goldilocks zone, or habitable zone, was defined as the region around a star, where an Earth-like planet could maintain liquid water on its surface. But what if the most common habitable environments in the galaxy aren't Earth-like at all? What if they're the deep oceans of water worlds, protected from stellar radiation and cosmic impacts, with stable temperatures and pressures that change only gradually over billions of years? If life can evolve and thrive in such environments, and Earth's deep-sea ecosystems suggest it might, then the habitable real estate in our galaxy could be far more extensive than we've assumed. Planets that we might dismiss as uninhabitable based on their surface conditions could harbor thriving biospheres in their deep oceans. This possibility forces us to expand our conception of what constitutes a habitable world. It suggests that in our search for life beyond Earth, we should cast a wider net, looking not just for Earth twins, but for a diverse array of planets that might support life in forms we've barely imagined. Third, water worlds offer a humbling perspective on Earth's water resources. Our planet appears blue from space, with oceans covering 71% of its surface. We think of Earth as a water-rich world. But compared to planets like TOI 1452b, our water supply is modest indeed, less than 0.1% of our planet's mass. This perspective highlights the precious nature of Earth's water balance. We have enough water to support diverse ecosystems, from deep oceans to shallow seas, from rivers and lakes to wetlands and rainforests. But not so much that the entire surface is submerged beneath a global ocean hundreds of kilometers deep. This delicate balance has allowed complex life to evolve and thrive on Earth's surface, including the human civilization that now spans the globe. It's a balance we're now altering through climate change, pollution, and overuse of freshwater resources. Water worlds like TOI 1452b remind us that planets can take many forms, and that Earth's particular configuration, with its mix of oceans and continents, its moderate temperatures, and its thin life-supporting atmosphere, is just one possibility among many. It's a configuration that has proven remarkably conducive to complex life, and one that deserves our protection and stewardship. Fourth, the discovery of water worlds expands our imagination about what life might be like beyond Earth. If planets with global oceans hundreds of kilometers deep are common, then perhaps the most prevalent form of life in the galaxy isn't surface-dwelling but aquatic, creatures that have evolved in perpetual darkness under crushing pressures, extracting energy from chemical gradients rather than sunlight. Such life would be fundamentally different from most life on Earth. It might organize itself in ways we can barely comprehend, developing senses, communication methods, and perhaps even forms of intelligence utterly unlike our own. This possibility reminds us that in our search for extraterrestrial intelligence, we should be open to forms of mind that might be radically different from human consciousness. Intelligence might emerge not just in air-breathing, land-dwelling organisms with vision as their primary sense, but in beings adapted to entirely different environments, with entirely different ways of perceiving and interacting with their world. Finally, water worlds like TOI 1452b highlight both the progress and the limitations of modern astronomy. Just 3 decades ago, we didn't know for certain if planets existed around other stars. Now, we're not only finding them by the thousands, but determining their compositions and contemplating their habitability. This progress represents one of humanity's greatest scientific achievements, the ability to detect and characterize worlds orbiting stars trillions of miles away. It's a testament to human curiosity, ingenuity, and our drive to understand our place in the cosmos. Yet these discoveries also remind us of the vast distances that separate us from even the nearest exoplanets. TOI 1452b, at 100 light-years, is relatively close in cosmic terms, but it's still so distant that sending even a robotic probe would be far beyond our current capabilities. For the foreseeable future, our exploration of these worlds will be limited to remote observations, powerful telescopes that capture the faint light from distant planets and extract from it what information they can. We will build increasingly sophisticated models based on this limited data, but much about these worlds will remain speculative. This limitation isn't cause for disappointment, but rather for wonder. It reminds us of the vastness of our galaxy and the countless worlds it contains, worlds we can study from afar, but may never visit in person. It reminds us that the universe is not just larger than we observe, but larger than we can observe, full of mysteries that future generations will continue to explore long after we're gone. In this sense, water worlds like TOI 1452b represent not just scientific discoveries, but symbols of humanity's ongoing journey of cosmic exploration, a journey that has no end, only ever-expanding horizons of knowledge and wonder. Throughout human history, we've gazed at the stars and wondered about our place in the cosmos. Are we alone? Are there other worlds like ours? Is Earth unique or common? The discovery of TOI 1452b and other water worlds brings us to a profound realization, a mind-blowing perspective that changes how we see our cosmic home. Earth is not the rule, it's the exception. Our planet, with its delicate balance of land and sea, its thin atmosphere, and its moderate temperatures represents just one possibility among countless planetary configurations. And it might not be the most common type of potentially habitable world in our galaxy. Water worlds like TOI-1452b suggest that planets with global oceans, worlds where water makes up a substantial fraction of their mass, might be abundant throughout the Milky Way. These oceanic super-Earths could outnumber planets like our own, creating a galaxy where the typical abode of life is not a rocky surface under a blue sky, but a deep, pressurized realm of perpetual darkness. This realization forces us to reconsider one of humanity's oldest questions. Are we alone in the universe? If water worlds are common, and if life can evolve in their vast oceans, then the galaxy might be teeming with aquatic biospheres, realms of life utterly unlike our familiar surface world. These biospheres would be protected from cosmic radiation by kilometers of water above. They would be insulated from temperature extremes and the impacts of asteroids and comets. They might provide some of the most stable environments for life anywhere in the galaxy. In such a universe, Earth-like planets with surface dwelling, technology-building civilizations might be the cosmic oddity, rare islands of complexity in a galaxy dominated by water worlds and their deep ocean biospheres. This perspective inverts our traditional view of habitability. Instead of seeing Earth as the template for life-bearing worlds, we might need to recognize it as an outlier, a planet with just enough water to support diverse ecosystems, but not so much that its entire surface is submerged. And this leads to an even more mind-bending possibility. What if the most common form of intelligence in the galaxy isn't surface-dwelling, but aquatic? What if the typical mind in our cosmic neighborhood has evolved not to manipulate tools or build fires, but to navigate the three-dimensional realm of a global ocean? Such intelligence might perceive the universe very differently than we do. Without easy access to fire or metallurgy, it might never develop the technology to leave its watery home. Without a clear view of the stars, it might be unaware of the broader cosmos. It might evolve forms of communication, art, and philosophy utterly unlike our own, shaped by the unique conditions of its aquatic environment. If this is the case, then the galaxy might be full of intelligent beings who will never contact us, not because they don't exist, but because they've evolved in environments that make technological civilization, as we understand it, impossible or unnecessary. This possibility suggests a profound cosmic irony. The very conditions that make Earth so conducive to the evolution of technological intelligence, its mix of land and sea, its oxygen-rich atmosphere, its moderate gravity, might be relatively rare in the galaxy. We might be able to search for extraterrestrial intelligence precisely because we evolved on an unusual world. But there's another possibility, one that's even more mind-blowing. What if intelligence has evolved on water worlds, but in forms so alien that we wouldn't recognize it as intelligence at all? Imagine vast networks of interconnected organisms spanning different ocean layers, sharing resources and information across pressure and temperature gradients that no single organism could traverse. These networks might function as distributed intelligence systems, not centralized brains as we understand them, but consciousness emerging from the interactions of countless specialized nodes spread throughout a global ocean. Such intelligence would have no need for technology as we conceive it. It would have no concept of tools or machines. It might experience the universe as patterns of chemical signals, pressure waves, or electrical fields, a mode of perception utterly unlike our vision-dominated experience. If such forms of intelligence exist on water worlds throughout our galaxy, we might be surrounded by minds we cannot comprehend, living on planets we've categorized as potentially habitable, without recognizing the complex consciousness they might harbor. This perspective challenges our anthropocentric view of intelligence and our assumptions about how minds might evolve on other worlds. It suggests that in our search for extraterrestrial intelligence, we might need to look not just for technological signatures like radio signals or megastructures, but for patterns and processes that might indicate the presence of consciousness in forms radically different from our own. And this brings us to the ultimate mind-blowing realization. The universe is not just stranger than we imagine, but stranger than we can imagine. The diversity of worlds in our galaxy, from rocky planets like Earth to water worlds like TOI 1452b, to gas giants and beyond, hints at a cosmic creativity that exceeds our limited perspective. Each of these worlds represents a unique experiment in planetary evolution, shaped by its particular history, composition, and environment. Each might harbor life forms adapted to its specific conditions, and each might give rise to forms of mind that perceive and interact with the universe in ways we can barely comprehend. In this vast cosmic ocean of possibilities, Earth is just one island, precious and unique, but not the template for all that might exist. Our perspective is just one way of experiencing the universe, valuable and valid, but not the only possible mode of consciousness. This is the profound gift of exoplanet astronomy, not just the discovery of distant worlds, but the expansion of our cosmic perspective. It reminds us that the universe is far richer and more diverse than our limited experience suggests. It invites us to transcend our Earth-centric view and embrace the incredible variety of worlds that populate our galaxy. And it challenges us to imagine forms of life and mind beyond our familiar experience, to recognize that the cosmic ocean might harbor consciousness in forms we've never dreamed of. On worlds like TOI 1452b, with its unfathomable depths and alien conditions. This is not just a scientific realization, but a philosophical one, a perspective that changes how we see ourselves and our place in the cosmos. It's a reminder that we are part of something far larger and more diverse than we can comprehend, a universe of endless possibility and wonder. As we come to the end of our journey through the deep oceans of TOI 1452b, let's take a moment to reflect on what we've learned and what it means for our understanding of the cosmos. We began with a simple observation: a planet 100 light-years away with a density suggesting it could contain substantial amounts of water. From this basic data point, we've explored the implications for planetary formation, the potential for life in extreme environments, and the profound philosophical questions raised by the existence of water worlds. Here are the key takeaways from our exploration. TOI 1452b represents a type of planet with no analog in our solar system, a super-Earth with oceans that could be 30 times deeper than Earth's, where water might make up to 30% of the planet's mass. Such water worlds challenge our understanding of planetary formation, suggesting that planets can evolve along pathways very different from those that shape the 8 worlds of our solar system. The deep oceans of water worlds might provide stable, protected environments where life could evolve, perhaps in forms utterly unlike the surface-dwelling organisms of Earth. If water worlds are common, as some evidence suggests, then the typical habitable environment in our galaxy might not be an Earth-like surface, but rather the deep oceans of these aquatic super-Earths. This possibility expands our conception of habitability and forces us to consider forms of life and intelligence that might evolve in environments radically different from our familiar surface world. Earth, with its delicate balance of land and sea, might be relatively unusual, a cosmic outlier rather than the template for life-bearing worlds. These realizations don't diminish the value of our home planet, but rather enhance our appreciation for its unique characteristics and the precious balance that makes it so conducive to complex life. As we continue to discover and characterize exoplanets, our understanding of cosmic diversity will only grow, challenging our assumptions and expanding our perspective on what planets can be and what forms life might take throughout the galaxy. This journey of discovery is just beginning. With new telescopes and instruments coming online in the coming years, we'll gain ever more detailed views of distant worlds like TOI 1452b. We'll analyze their atmospheres, determine their surface conditions, and perhaps even find evidence of life beyond our solar system. And you can be part of this journey by staying informed about exoplanet discoveries, supporting scientific research and space exploration, and contemplating the profound implications of these findings. You're participating in one of humanity's greatest adventures, the exploration of our cosmic neighborhood and the search for our place within it. If you've enjoyed this exploration of TOI 1452b and the mysteries of water worlds, please consider subscribing to our channel. Hit that notification bell so you don't miss our future deep dives into cosmic mysteries. And if you found this content valuable, please share it with others who might appreciate this journey through the wonders of our universe. What do you think about water worlds like TOI 1452b? Do you believe they could harbor life? What forms might that life take? Share your thoughts in the comments below. We'd love to hear your perspective on these cosmic mysteries. Thank you for joining us on this journey through the deep oceans of a distant world. Until next time, keep looking up and wondering about the incredible diversity of planets that populate our cosmic neighborhood, each with its own story, its own possibilities, and perhaps its own unique forms of life waiting to be discovered. The universe is vast, diverse, and full of wonder, and we're just beginning to explore its depths.